Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University, Gwalior. Today, in this module, we shall study ion exchange methods under the paper Fundamentals of Analytical Chemistry. Ion exchange is a reversible process in which we can regenerate the ion exchange which is being used for the separation of different types of ions. Weakly acidic cation exchangers are prepared by introducing carboxylic acid functional group on a polyacrylic acid matrix. On the other hand, weaker anion exchangers can be prepared with secondary amines yielding a weakly basic tertiary amine. So this ion exchange mechanism, earlier it was noticed that in clays, ion exchange process was noticed in clays. So observing this natural behavior, synthetic ion exchangers were prepared, cation exchangers and anionic exchangers were prepared. And one of the specificity of these exchangers is that cation exchanger will exchange cation, anion exchanger will exchange anion. It is the exchange of similar type of ions. Many natural clays are able to function as ion exchangers because they are insoluble polymeric materials with a loose structure and many replaceable metal ions. A continual exchange of ions takes place between these clays and the waters passing through them. The detailed process is modified and complicated by the pH and carbonate content. Clays have varied and unpredictable properties, and it was only with the introduction of synthetic ion exchangers that a reproducible scientific technique became possible. Modern ion exchange resins were first used in 1935 by Adams and Holmes. These resins consist of three-dimensional network of polymeric chains cross-linked with short chains containing ionizable functional groups. Thus, there is an insoluble phase with fixed ionic sites of one charge, while the oppositely charged species are free to move about in the solvent and be replaced by other ions of like charge, provided that electroneutrality is maintained. These resins can be used either in a batch process for a wholesale exchange of ions with those in solution or packed into a column and used in a chromatographic fashion. They have proven invaluable in the separation of ionic substances with closely similar chemical behavior. Types of resins. A typical resin is prepared by a polymerization of styrene and divinyl benzene as shown in the following equation. The above structure is repeated in three dimensions with the number of cross linkages determined by the ratio of divinyl benzene to styrene. Increasing the cross linking increases the rigidity, reduces swelling, reduces porosity, and reduces the solubility of the polymeric structure. Ordinarily, about 10% divinyl benzene is used, but both higher and lower percentages are available in commercial resins. The particle size of the product is determined largely by the extent of mechanical agitation during the reaction, so that resin beads of numerous grades sizes are available. Cation exchangers. Acidic functional groups are easily introduced, for example, by sulfonation, in which a sulfonic acid group is attached to nearly every aromatic nucleus. Sulfonic acids are strong acids with essentially completely dissociated protons, although these protons are not free to leave the resins unless replaced by other positive ions. Weakly acidic cation exchangers are prepared by introducing carboxylic acid functional groups on a polyacrylic acid matrix. The total number of equivalents of replaceable protons per unit volume of resin determines the exchange capacity of the resin. For weak ion exchange resins, the capacity is a function of pH. If basic functional groups are introduced, the resin can exchange anions rather than cations, and such type of resins are known as anionic exchangers. Strong anionic exchangers are prepared with a tertiary amine yielding a strongly basic quaternary ammonium group. Weaker anionic exchangers can be prepared with secondary amines yielding a weakly basic tertiary amine. A few common resins are tabulated in Table 1. The another important property of ion exchanger, which may be cation exchanger or anion exchanger, is the swelling. That on taking the molecules of water, it swells. The high proportion of polar groups within the resin gives a hygroscopic character. In a sulfonate resin, one can consider that the SO and H plus ions dissolve in the adsorbed water, yielding a solution of high concentration. Since the ions cannot diffuse out, there is a tendency for water to diffuse in to equalize the concentration, but the amount of water that can diffuse in is restricted by the space available in the inter, inter, intercases of the resin structure. And in this way, if they swell, exchange of ions takes place, exchange of cation or exchange of anion takes place. In this case, when it is the H plus ions are present there, then the exchange of another cations will take place with this type of resin. The important properties which determine the behavior of a resin are size of particles, rate of exchange, and permeability of the packed column, degree of cross-linking, rigidity, porosity, swelling, nature of functional group, kind of ion exchange, strength of functional group, distribution coefficient, number of functional groups, capacity of resin. If we consider the theoretical principle involved in the exchange of ion, we should consider the net result of an ion exchange reaction, which can be expressed as a replacement of equivalent quantities of like charged ions. It is important to mention here that the word like charged ion means positively charged will replace positive ion, negative ion will replace negative ion. For example, HR plus Na positive will form NaR and protons will be liberated means sodium ions has in place of sodium ions which is positively charged hydrogen ions are being replaced. Similarly, in case of 2HR plus calcium plus 2, it will form CaR2 plus 2 plus ions. Means here two ions are replaced because two positive ions of hydrogen, two protons are replaced because here calcium is having two valency. Calcium plus 2 we have taken. In case of again RCl, OH minus is replaced by Cl minus means like charge ions are replaced or we can say replacement of equivalent quantities of like charge ions where R plus or R1 represents the resin matrix. A complex resin matrix has been represented by R or R dash. The law of mass action and therefore the equilibrium constant or the selectivity coefficient takes the usual form as shown in the following equation, where K is a constant only if the activities of the various species are used. Otherwise, it will vary with relative and total concentrations due to changes in activity coefficients. Selectivity coefficients defined by neglecting activity coefficients are determined empirically and are reasonably constant for a given condition. Experimental observations have been formulated into a number of useful rules, which are as follows. Number one, Selectivity coefficients approach unity as the cross-linking is decreased. The exchange of ions that causes expansion of the resin is less favored than those exchangers that do not, or the smaller the ion, the greater the affinity for the resin. The greater the charge on the ion, the greater the affinity for the resin. The affinity of high molecular weight organic ions and some anionic complexes of metal ions are unusually high, probably because the electrostatic forces are augmented by short range adsorption, that is, van der Waals forces. To a first approximation, these rules predict the observed order of affinity for groups of ions as shown in the following scheme. That is, from lithium we start, it will either go on increasing through proton, through sodium, ammonia, and it reaches maximum at barium 2 in the first series, in the second series. So it follows the groups of ions as shown in the following scheme. The above orders often show inversions due to change in pH, relative concentrations, nature of resin, complex formation, ionic strength. The above order which has been shown is not strictly followed, but it may change if there is changes in pH, relative concentrations, complex formation is taking place, ionic strength varies, then the above order may change. The plate theory developed by Martin and Singe for partition chromatography can be applied directly to an ion exchange column with only a change of terminology. Here we will define a distribution ratio D ratio as D is equal to quantity of sample in resin of a given plate upon quantity of sample in interstitial solution of a same plate. The volume of eluent required to move the sample through the column measured to the peak is maximum and is represented by the following equation, where Vm is the interstitial volume of the column. Let us assume the samples contains cations A plus and B plus, which are to be separated from each other. When the sample is introduced, it is first retained at the top of the column by exchange of cations. So we have assumed here cations A and B are present here, and when the sample is introduced, it is first retained at the top of the column by exchange of cations. A plus cations plus HR is in equilibrium with AR and protons released. B plus HR again HB are formed and H are released. The corresponding selectivity coefficients are for Ka and Kb are shown in the following equations. A separation factor alpha A upon B can be derived from above equation and is represented as in the following equation. In equations, we have neglected the activity coefficient, but to a first approximation, the last equation tells us that the separation factor is independent of concentration of other ions. Now the cations A plus and B plus can be eluted from the column only if they are replaced by another cations contained in the eluent. In this case, let us assume that the eluent contains a high concentration of H plus. Equations show that increasing H plus must also increase A plus and B plus. In other words, we can change the distribution ratios for A plus and B plus and thus the elution volume manifold by altering the concentration of eluting ions. That is, cations A ratio for cations of A and cations for V, and thus the elution volume may fold by altering the concentration of eluting ion. A high concentration of the latter will lead to faster elution with sharper but less well-resolved peaks as shown in figure 1. Separation of potassium and magnesium is taking place. Here, place of A plus and B plus, the potassium and magnesium ions are being separated, which are very difficult to separate by other techniques. Effect of pH. The extent of dissociation of weak acids and bases and the hydrolysis of salts and metal ions is controlled by the pH of the medium. Thus, the electrical charge on a species may be increased, decreased, or even reversed by a change in pH. In this manner, a delicate but powerful means of influencing the distribution or of preventing exchange together. This behavior is especially important in the separation of amino acids, which can carry a positive, negative, or no net charge depending on the pH of the eluent. Buffered eluents are obviously indicated for separations of this kind, but one must not forget that the ionic constituents of the buffers are also subject to exchange with the resins so that the pH within the column may bear no relation to that which was prepared. The effect of pH on the elution of a typical weak acid has been shown in figure 2. In the above figure, we can very well see the effect of pH on the elution of a weak acid anion on an anion exchanger. Plot is milliliter of eluent versus concentration. Effect of complexing agents. Ligands, which are neutral molecules, have no effect on the charge of an ion, but they change the exchange equilibrium constant. Many metal ions are complexed by anions, yielding negatively charged complex ions. Thus, the rare earth metal cations, which are poorly separated by cation exchangers, can be complexed and separated quite well by anion exchangers. Most of the useful complexing agents are themselves weak acids, weak bases, or anions or cations thereof. Similarly, selection and preparation of the resin is very important. How to select a resin, how to prepare a resin. A wide variety of resins are available commercially, from which one must select an appropriate mesh size, cross-linking, and quality. Analytical grade resins are preferred because they have been more carefully sized and washed to remove foreign organic and inorganic materials. It may be necessary to convert the resin from one form to another. It is important to know if it is important to know the weight of the resin used. It must be dried or brought to a known moisture content in a hygrostat, that is, in a vessel with controlled constant humidity. In any event, before packing, it must be equilibrated with water by prolonged soaking. After the resin has settled, the fines which float in the water are poured off. Packing the column. Uh, Simple columns are constructed from glass tubing with a reservoir at the top for the eluent and a frit disc at the bottom having a glass wool. So while packing the column, it is very important that there should be no gas bubble in the column. For that purpose, a slurry of the exchanger is taken and then by tapping it is filled the column. The resin is packed in a generally as an aqua slurry and allowed to settle with occasional tappings, which is very important. Tapping and taking aqua slurry is very important. Total capacity of the column. A very important parameter is the total exchange capacity of the column, which influences the maximum sample size and is used to check the long-term stability of the resin. The capacity of a resin in milliequivalents per gram of dry resin is normally marked on the bottle by the manufacturer. Experimentally, it is most readily determined by converting the resin directly to the hydrogen form and then eluting with a sodium chloride solution until it is completely converted to the sodium form. The effluent then must contain hydrochloric acid in an amount equivalent to the capacity of the column, easily determined by titration with sodium hydroxide. Common resins have a capacity of 1 to 5 milliequivalent per ml or roughly 1 to 5 N in acid or base. Detection method. The difficulty of detecting small amounts of sample components in the presence of a large concentration of eluting ion is one of the major disadvantages of ion exchange methods. Continuous recording is not common, although in specific applications, light absorption, refractive index, pH, radioactivity, or polographic measurements have been utilized. The most common practice is to collect numerous small equal volume fractions and analyze each fraction for the species sought. Applications of the technique: removal of ions. The household water softener is perhaps the most common example of ion exchanger. Calcium, magnesium, iron, and all other multiply charged cations are replaced with sodium ion. The softened water then contains sodium salts, which are innocuous in plumbing systems and for most home uses. Sodium is chosen because it is harmless in the water and because the resin can be readily regenerated with a strong solution of common salt. Completely deionized water is prepared by passing the raw water through a cation exchanger which replaces all cations with hydrogen ion and then through an anion exchanger which replaces all anions with hydroxide ion. In effect, the salts are replaced with ions of water. The two resins can be combined in a single mixed bed so that the water never becomes too acidic or basic as it might if passed through the two resins separately. Deionized water having conductivity of less than 10 raised to power minus 6 per centimeter is prepared more conveniently by ion exchange than by distillation. However, deionization process does not remove non-electrolytes and thus the water may still be quite impure. Ion exchange offers a convenient and effective method for desalting solutions of organic or biochemical mixtures. The removal of one or more interfering ions by replacement with an innocuous ion for a given process or procedure is an obvious application. The determination of total salt content of a solution is simplified by conversion of the ions to hydrogen ion or the anions to hydroxide ion followed by simple acid-base titration. Whenever a trace amount of an ion must be isolated or concentrated from a large volume of aqueous solution, one of the methods of choice is to remove it with an ion exchanger followed by elution into a small volume of eluent. This is common step in the determination of trace metals in water, copper in milk, or the recovery of precious metals. Perhaps the most spectacular example occurred in the isolation and identification of the first sample of Mendelevium. 10,000 atoms of Einsteinium on a gold foil were bombarded with high energy alpha particles. The target was quickly dissolved with aqua regia and the gold extracted with high acetate. The aqueous phase, which contained the Einsteinium and any Mendelevium produced, was separated with miniature ion exchange columns. At one point, the entire world supply, about 17 atoms of this newly discovered element, was contained in a single resin bead. Preparation of reagents. Determinate solutions of strong acids and bases are not easily prepared because of the lack of primary standard reagents. On the other hand, primary standard sodium or potassium chloride is readily available and their solutions are stable indefinitely. A liquids of these solutions, when passed through a resin in the hydrogen or oxide form, will produce equivalent amounts of acids or base. Many other solutions, which are difficult to prepare or standardize, can be made in a similar fashion. Next application and very important application is the separation of metals. Ion exchange is especially advantageous for the separation of metal ions with very similar properties for which specific methods are not available. For example, the alkali and alkaline earth metals are always difficult to determine in mixture but can be readily separated in an ion exchange column. The separation of rare earths is a classic problem formerly accomplished only by numerous and tedious fractional crystallizations. Ion exchange columns now provide pure rare earth compounds on a commercial scale. Another application is the separation of amino acids. The most impressive example of the versatility and potency of an ion exchange method is the separation of the complex mixtures of amino acids encountered in biochemistry. The amphoteric nature of this group of acids makes it possible to change the sign of the charge or to remove the net charge so that a given acid is amenable to exchange on a cationic or anionic resin or neither by controlling the pH of the solution. Thus, at a given pH, a mixture of amino acids can be separated into three groups according to their isoelectric points by passing it through the two types of resins successfully. After changing the pH, the groups can be further subdivided as many times as desired. Students, in this module, you have learned what are ion exchangers, how ion exchangers can be prepared, how ion exchangers can be functionalized for cationic or anionic group, how what is ion exchange chromatography, by using ion exchange chromatography, how different rare earths, different elements having close related properties can be separated. Here, again, I can say ion exchange is an exchange of ions between two electrolytes or between an electrolyte solution and a complex. In most cases, the term is used to denote the processes of purification, separation, and decontamination of aqueous and other ion-containing solution with solid polymeric or mineral ion exchangers. Typical ion exchangers are ion exchange resins, zeolites, monometronite clay, and soil humus. Ion exchangers are either cation exchangers that exchange positively charged ions, that is cations, or anion exchangers that exchange negatively charged ions, that is anions. There are also amphoteric exchangers that are able to exchange both cations and anions simultaneously. However, the simultaneous exchange of cations and anions can be more efficiently performed in mixed beds that contain a mixture of anion and cation exchange resins or passing the treated solution through several ion exchange materials. So this ion exchange process has many applications. Their particular applications are in the treatment of water, how to get water free of anions and cations. High quality of water may be prepared by the use of ion exchangers, and also its very beautiful use in the separation of substances, separation of elements like sodium and potassium, which have very close properties, very are similar in properties, and they cannot be separated by any other method, but they can be easily separated by ion exchange chromatographic method. Separation of rare earths, as I have explained here, is possible by ion exchange chromatography. So, ion exchangers, ion exchange chromatography has vast applications and is very important separation technique in analytical chemistry. Thank you.